Hi, this is Hassan Kurani. In this video, we are going to continue our lesson about scalar product in a plane required for grade 10. We still have to learn how to calculate the scalar product of collinear vectors, of orthogonal vectors, and how to calculate the cosine of geometric angle between two vectors. After that, we are going to see the application of cosine law using scalar product, and at the end we are going to see important and useful methods to calculate scalar product. Okay, the first point is about scalar product of collinear vectors. As you know, collinear vectors in a plane either have the same sense or opposite sense. So for that we consider two cases. The first case, as you see, we have two vectors drawn as an example in a way that they have the same sense. And as you know, what is the geometric angle between two vectors that have the same sense? From previous videos we saw that the geometric angle will be 0 in fact, and using the geometric angle between geometric definition of scalar product u dot v, it will be magnitude of u times magnitude of v times cosine alpha, or cosine 0 in this case. Cosine 0, as you know, using calculator is 1. So the result will be u dot v, it's magnitude of u times magnitude of v. We can directly apply this as a rule in case we have two vectors of the same sense. What if the two vectors have opposite sense? Still they are collinear but of opposite sense. As you know, the geometric angle between them is 180 degrees or pi radians. For this reason, applying the geometric definition, u dot v, it will be magnitude of u times magnitude of v times minus 1. From where we got this minus 1? This is in fact from cosine alpha factor, the term cosine alpha, cosine 180. As you know, using calculator again, you can easily get minus 1. For this reason, we can apply this again directly in our exercises. Okay. Here we are going to see another case, special case, which is the orthogonal vectors. When do we have orthogonal vectors? You know, orthogonal is related somehow to perpendicular, but in vectors usually we use this term orthogonal since it's possible to have two vectors away from each other, so there's no intersection. For this reason we say orthogonal and we don't say perpendicular. Anyway, these two vectors, let's consider u and this is v, and as you see the geometric angle between them is 90. For this reason they are orthogonal, even in this position or that position, or even if they are intersect each other, perpendicular or orthogonal. In all cases we can say they are orthogonal vectors. Or possibly we have them in this position, as you see, in this position or that position. Okay, I think it's very clear to you that two vectors are orthogonal if as you will see here, if they are two non-zero vectors u and v are orthogonal, and we write this symbol as perpendicular with a little dash under it. This means that this operation of this symbol is used for the orthogonality of two vectors if the geometric angle between them is what? Right, or 90 degrees. Thus we get the following equivalence: u orthogonal to v if and only if u dot v equal to 0. Why we have u dot v equal 0? I think it's clear from the geometric definition, which is magnitude of u times magnitude of v times cosine 90. As you know, right is 90 degrees. Cosine 90, as you know, is 0. For this reason, u dot v, it will be 0. These two propositions are equivalent. Now, note that in an orthonormal system, OIJ, you know, in an orthonormal system, I and j will be orthogonal vectors. For this reason, we can directly say that I dot v is equal to 0, and I dot I, it's in fact magnitude of I square. As you know, from previous particular case, we took u dot u, it's magnitude of u square, and here u dot u, it's magnitude of I square. And as you know, it's an orthonormal system, and the magnitude of I is 1 unit, magnitude of j is also 1 unit. For this reason, we directly can notice that the I dot I is 1 and j dot j is also 1, or j square magnitude of j is 1. 1 square is also 1. Okay, that's it. Let's see these examples. We are given u 2 radical 3 and v of coordinate 6 minus 4 radical 3, and we are asked to verify that u is orthogonal to v. To do this, as you see, we are given coordinates, so it's easier for us to use the analytic definition, which is x prime plus y prime, x times x, which is 12, and radical 3 multiplied by minus 4 radical 3, which is minus 12. As a result, we got 0. Since u dot v is 0, this means that u is orthogonal to v, and the geometric angle between them is 90, although we don't have the graphical representation of u and v. And we no need to draw them or place them in an orthogonal system. Here we have another good application, and it's useful for us in our exercises and our homeworks. Given the points A, B with unknown abscissa A minus 1 of ordinate 4, and C 0, 2, and D 1 minus 1. We are asked to calculate this value, this unknown A, so that the two straight lines BD and AC are perpendicular. Try to think about a way to find A. Try to use this given. As you see, we are given the lines BD and AC are perpendicular. What relation do we have if the straight lines are perpendicular? Probably you are thinking about the vectors and try to choose the convenient suitable vectors in this case. Here, as you see, the suitable vectors are in fact BD vector, which is placed on the line BD, and AC vector, which is on the line AC. Okay, we can find the coordinates of BD and AC. As you see, we chose BD since we are given the line BD and AC are perpendicular. For this reason, we chose these two vectors. You can easily know how to calculate the coordinates of BD, knowing coordinates of B and D, and similarly AC can be calculated easily. After this, now the perpendicularity of these two straight lines leads to what about these two vectors? This leads to have BD and AC as vectors will be sure orthogonal. The geometric angle will be orthogonal. And using the equivalence as above, two vectors are orthogonal, then their dot product, their scalar product will be what? Will be 0. And since we are given the coordinates of these two vectors, we can easily apply the analytic definition, which is x prime plus y prime, which is 0. And after calculation of this side of this equation, we are going to get at the end the value of A, which is 26/3 in this case. Okay, this is our homework, and we are going to continue the next idea, which is cosine of the angle of two vectors. It's quite easy. If we have two vectors in a plane, u and v, and alpha is the geometric angle between them, from the geometric definition, as you know, u dot v, it's magnitude u times magnitude of v times cosine alpha. We need this term. We are given in this in such cases usually u dot v and magnitude of u of magnitude v. you can easily find cosine alpha. Just divide by magnitude of u times v both sides. To get cosine alpha, it will be u dot v over magnitude of u times magnitude v. Sure, we said here two non-zero vectors, and this is important in order not to get a zero in the denominator. Since you know zero vector, its magnitude is 0, and this will be 0, and at the end we get non-defined fraction. So it's direct. We can just derive it from this definition. Let's see further idea. If you have u and v with their coordinates in an orthonormal system yj, then we obtain another form for this formula, which is cosine alpha. It will be equal xx prime plus y prime, which is u dot v. And as you know, we have the coordinates of u, so the magnitude of u will be radical square root of x squared plus y squared multiplied by the magnitude of v, which is square root of x prime squared plus y prime squared. Okay, let's see a direct example on it. Okay, we are given the 3 points A, B, C, and we are asked to calculate cosine BAC, which is the geometric angle between BAC. Now, let me tell you that it's no need to plot these points in an orthonormal system. You can first, you must think about choosing the suitable vectors in this case. As you know, as we see before, cosine of angle is the scalar product of vectors over the magnitude of this times the magnitude of this vector. Now, your mission is to find the suitable vectors required to calculate this cosine BAC. Okay, which vectors are suitable in this case? Well, if you think about AC, BA, it's very easy. You can see that you must, the vertex of this angle is A. Thus, stand at A and move in a way on a left and right, then you can get easily the vectors, the suitable vectors, which are AB vector and AC vector, or AC and AB, never mind. In both cases are true. As you see, we can easily find the coordinates of AB and AC. And as I said, you stand at the vertex, choose the vertex. If you don't have any drawing, you are just giving these data in here, AB.AC or AC.AB. By this way, we are applying the rule directly. It will be AB.AC over magnitude of this times the magnitude of this vector. At the end, we can easily calculate this AB.AC, this term, which is xx prime plus y prime, 16 minus 5, which is 11, over square root of magnitude of AB times AC to get this result. Hence, as you know, by this calculation we got cosine of BAC, which is 11 over this number. So to get BAC, it's a matter of calculation using calculator. It's cosine minus 1, cosine inverse, which is using calculator, you can just shift cosine of this value to get the angle itself. Well, this is a note, cosine alpha equal A over B, which is a number between -1 and 1, as you know, since cosine is between -1 and 1. Then alpha will be cosine minus 1, which we can use the calculator to get it, cosine minus 1 of AB to get the angle. Here we have approximated angle, which is 65 degrees, 65.4 degrees. Okay, this is our homework according to these what we said before, and I prefer to stop here Next time we are going to talk about cosine law, and we will see some useful methods to calculate scalar product. Thank you for watching. Goodbye.